Good. So the second topic of this session will be about Proto-Quipper with dynamic lifting, and the speaker is Frank Fu.
All right, thank you. Good morning, everyone. I'm Frank Fu. Today I'm going to talk about Proto-Quipper with dynamic lifting. And this is a joint work with my co-authors, Kohei Kishida, Julien Ross, and Peter Selinger. So first, I'd like to give you a brief introduction to Quipper and Proto-Quipper. They are quantum programming languages. They're designed for programming quantum circuits. So here is a high-level overview of the compilation process of Proto-Quipper. So as we can see, in this compilation process, we distinguished two runtimes. The first one is called circuit generation time. It's responsible for compiling the high-level program to a low-level quantum circuit. And the circuit generation time can be done entirely in a classical computer. So we don't need quantum computer to generate circuit. Whereas in the second runtime, which we call circuit execution time, it's responsible for sending the circuits that are generated to the actual quantum computer or a quantum simulator. And it's also responsible to send back the results to the classical computer. So there are values that are associated with these two runtimes. In the circuit generation time, we have values such as natural numbers, Boolean. And these values are duplicable. They are parameters of some kind. And whereas in the circuit execution time, we have values such as qubit and bit. These are considered linear objects, so they cannot be duplicated and so on. And you can think of values in the circuit execution time as internal a state that is internal to the quantum machine. So the value between these two runtimes, they do interact. So for example, if we know we can initialize a qubit from a Boolean. So if, for example, if the Boolean is true, then we can insert an initialization gate to initialize a qubit in the 1 state or in the 0 state, depending on the Boolean value. But the other direction is more subtle. By that, we also need a way to get the bit value from the quantum machine back to the programming language as a Boolean. In our case, we call this particular mechanism to lift a bit value to a Boolean in the programming language. We call it dynamic lifting. It's a mechanism that is also appeared in the programming language Quipper. So this operation is important because a lot of the time when we send a circuit to the quantum computer, the quantum computer will execute the operation specified by the circuit. And the only way to get the results of the quantum computation is through measurement. So, and the results of the measurement in a quantum computer will give us bit value. So in that case, the ability to lift the bit value to the Boolean in the programming language allow us to use the results returned from the quantum computer. And in fact, the main contribution of our paper is to develop the categorical model and a type system for this particular operation. Now, I have already talked about the two runtime, and we can in fact model the assumptions of these two runtimes as categories. So for the content circuit, we can model it by a symmetric monoidal category. We call it N, where the morphism in this category, they are boxes. You can think of them as boxes. And the object in this category, they are wires. So connecting boxes with wires, we get the category of content circuit. And another category that we can assume is a category of content operations. So this we denote it by Q. So the morphism in this category will correspond to the content operation that a quantum machine can do. So it's fairly physical. And the object in the category Q, they correspond to the state in a quantum computer. So the fact that we can send the quantum circuit to a quantum machine so that the quantum machine can execute it can be modeled as an interpretation functor, J, from M to Q. Now we want to give a categorical model for dynamic lifting. And in particular, we want to model typing judgment as a morphism in a single category. So the way we do that is we will construct a new category, which we call A in this case, and it is equipped with a monad T. And we construct the category A in a way such that this following commutative square holds, right? So this diagram is basically saying that we can embed the category of quantum circuit into our new category A, whereas the content operation, on the other hand, it can also be embedded, but not to category A, but to the Claesley category of A. So this way, the category A, in a way, have a notion of quantum circuits, and at the same time, it also has a notion of quantum operation in the same time. And therefore, we can model dynamic lifting as a morphism from bit to T of bool, such that the following diagram commutes. So the meaning of this diagram is essentially this. If we start with a Boolean parameter, we can initialize a bit state based on the Boolean parameter. And then if we lift this bit back to the programming language as a Boolean, that should be the same bool that we are started with. So that's roughly the meaning of this commutative triangle. Now on the type system side, we are going to add a notion of modality for dynamic lifting. So for each typing judgment, we associate it with a modality alpha, and alpha can have values 0 or 1. So the meaning of this is that the modality indicates the use of dynamic lifting. So that's one way to see the meaning of this modality. So for example, if we look at the rule for dynamic lifting, it says that if n has type bit, then we can lift this bit to bool. But then the only difference is that the modality alpha is set to 0. So it means that the dynamic lifting occurs. Okay. Another way to look at this notion of modality is the idea of boxing in Proto-Quipper. So in Proto-Quipper, when we program quantum circuit, the idea is that if we have a circuit generation function of the right form, in this case, if we ignore the indexes 1 in the type, so we're just saying if we have a linear function from S to U, then we can generate a circuit. So this might sound a little abstract, but let me now show you what it actually looks like in practice with this boxing. So now I'm going to switch my screen to an Emacs editor. So here is a function that we can define in Proto-Quipper. It's called tally1. So it has the type qubit to qubit. In fact, it's a circuit generating function. So in the next line here, we can define the circuit with input qubit and output qubit, and we can box the tally1 into a circuit. And so that's the boxing in practice. And in fact, we can see what the circuit looks like by performing by typing a command in the terminal. So that's roughly what the circuit looks like. That's the results of the boxing. Close this, and then I'll go back to the slide. So that's boxing, okay? So then we return to the indexes. So we have 1 in the type. So it just means that when we box the circuit generating function, we want to make sure that this circuit generating function does not use dynamic lifting, because dynamic lifting is a concept that is lifting the value from execution time to circuit generation time. So it's in our case, we cannot box it as a circuit. So then the rest of the typing rules are relatively standard. In fact, we have a type system to check the modality, and you can take a look at the more detail of the type system in our paper. But roughly, the idea is that here, when we form a lambda abstraction, the modality for a lambda abstraction is 1 because it's already a value, and value by itself does not perform dynamic lifting. Whereas the modality of n in the premises here will be lifted to the type, so that the type know that what the modality of m is. So that's reflected in this arrow type. And for the application type, for the typing rule for the application is similar. So because we are using a call by values strategy, so every part of the term in the application, they potentially could perform dynamic lifting. So the typing rule here, we make a Boolean conjunction of all the modality. So that's the typing rule. Now with the type system and the categorical semantics, we can then interpret typing rule into the categorical model. So for the typing judgment that has modality 1, we can interpret them as a morphism from gamma to A in the category A. Whereas when the modality is 0, we interpret as a morphism in the Claesley category of A. So in this case, it will be just a morphism from gamma to T of A, where T is the monad that introduced by the categorical model to model the dynamic lifting. So that's categorical semantics. We also specified operational semantics for our language. So in particular, because we have 2 runtimes, so we have to give evaluation rule for each runtime. So for the circuit generation time, the evaluation is deterministic. So we take a configuration in the circuit generation time, which is basically a pair of circuits and a program, and we run this configuration. And in the end, we get a new circuit and some value. So that's basically the evaluation process in the circuit generation time. Whereas for the circuit execution time, we also have an evaluation process, but because this runtime can perform measurement, because this runtime is supposed to model what's going on when we have a quantum computer. So the configuration in this case is also a pair. That is a pair of quantum state coupled with a program. So when we run this configuration, we get a possible distribution, a probability distribution of quantum states and value. So that's the main difference. So if we look at the evaluation rule for dynamic lifting, so how do we evaluate a Dyn lift of n? Well, we first evaluate n because by type preservation, we know M has type bit. So it will get evaluated to a new state, Q prime, and a pointer or label, if you will, point to the bit register. Then we can just read the value of L from the content state Q prime. So because this bit register can be a result of the measurement, so we get different value with certain probability. So that's where the non-determinism is coming from. Okay, so I can quickly show you what in practice, what we can do with dynamic lifting. So now I will again switch my screen to my Emacs editor. So in this case, so let me show you the bell pair. So here we have a Boolean circuit called bell00. It's basically generating, it's a circuit that prepare a bell state. So we can measure when we call this bell00, it returns 2 qubits, X and Y. We can measure the qubits, X and Y. They give us bits, and we can then lift those bits into Boolean so that we can see what the actual Boolean value is. So now in the interpreter, if I type in bell pair, it will actually return a pair of Boolean value. So what I'm trying to say is that with dynamic lifting, we can actually test small program to run a small program to see the actual value. Without dynamic lifting, we can only see the content circuit, but with dynamic lifting, we can actually run our circuits and do a few simple tests to see the value of the circuit. Okay, so that's my 1 minute quick demo. So to summarize, in our paper, we give a general categorical model for dynamic lifting, and we define the type system that use modality to check dynamic lifting, and we give operational semantics for the 2 runtimes, and we prove the type system and the operational semantics are sound with respect to our categorical semantics. So that's it. Thanks.
So the kind of boxing operator you use for circuits is restricted to functions which do not produce any lifting themselves. So can you elaborate a little bit on that, whether you think it's a real restriction, why you have to do that?
So if I understand, I'm not sure if I can hear you clearly. I think you're asking about me to explaining this box operation.
Yes. You know, in this box operation, to the left, you have S arrow U, and the effect of the arrow is 1. So I'm wondering, you know, whether you can put a 0 and what
right. Yeah, thanks for the question. Yeah, so it's actually crucial in our case to make sure this modality is 1 rather than 0. So if it were 0, it means that it's not a circuit generating function anymore because the function can use dynamic lifting, so it's doing something with the actual quantum computer. So in that case, we cannot actually box it into a circuit. So yeah, the actual modality constraint here is actually important. We need to require the modality for the arrow to have 1 modality. So it also means now the circuit is actually boxable. So 1 could mean boxability in that case. Thanks.
Okay.